Hello everybody, my name is Borsha and we will have some theoretical discussion about how we multiply matrices but using 2D array of threads. So, matrix multiplication using 2D array of threads inside one block. That's the name of the game. What is happening here? We have a result matrix. I forgot to put this on English, sorry, but this is let's imagine that this is result matrix, which we want to have from a multiplication of two other matrices, which are A and B. So we multiply A and B matrix to have result matrix C. And we are doing that job and business with the help of one block of threads, but using 2D array of threads. So we have threads in X and in epsilon and X-axis, and we want to use these indexes to pick up every thread if we need to manipulate with that thread. Also, what is need to say, what's need to be said, it's that every every thread representing a calculation of one element of this matrix. So one thread in this one block of threads, which is 2D block of threads, or 2D array of threads. This one block is 2D array of threads, is picking up and solving one element of this matrix, result matrix C. Of course, according to the rules for matrix multiplication. So in this case, all threads are inside one block. That's what we said. Also, don't forget that one block of threads is always executed on one streaming multiprocessor. So on one streaming multiprocessor, multiple blocks can be executed, but one block is always executed on one streaming multiprocessor, with the limitation for the streaming multiprocessor how many of these threads it can handle with. So just to be clear, so and also to follow the way we are going from a result matrix, which we want to calculate, two set of threads or one block of threads, and this is 2D array of threads. And that thread is a block of threads, which is 2D array of threads, is solved on one streaming multiprocessor always. Also, as we said, for each element of result matrix C, which we want to calculate, we want to create one thread which calculate that element. So I hope that everything is clear here. We are using one block, and that's the main topic, and we use a 2D array of threads in epsilon and X dimensions. So we can continue with the discussion. What is the name of the game? We are calculating one element of matrix C. Of course, according to the rules of matrix multiplication, because we are picking up one row from the matrix A with same index as the row in which is element of that matrix we want to calculate inside the matrix C. Also, we're picking up the column or one column inside of B, and same index for that column is on the matrix C. So you know the rules for the matrix multiplication. We're picking one row and one column. We multiplying respective elements, and also adding that multiplication to each other. So this is, let's say, visually represented what is going on here. So assumption is that we are doing matrix multiplication. We have entry matrix A, from which we are picking up rows, and entry matrix B, from which we are picking up columns, and result matrix for which we form threads with the respective indexes and corresponding indexes which are representing, let's say, elements of the matrix C. So don't forget. So how many threads, how many elements in the result matrix C, so many threads which are calculating that elements. For all 64, so 8 times 8 elements in the result matrix, threads need to be formed which are calculating those elements of result matrix. So we mentioned that before, and each element is created by multiplying and adding respective elements of row and of row of matrix A and the column of matrix B. So that's what is represented here. So I hope everything is clear. It's a basic, let's say, algebra. So we mention it so many times. I'm bored with it, but it's also good to be said again and again to have better imagination what's happening inside of it, to avoid any confusion which can be made by many of steps what we turning what into. So for every element we form a block of threads, 2D block of threads with indexes for the picking up indexes for the rows and columns, and have very well and properly indexed thread inside of that, let's say, 2D array of threads which are solving these elements. So everything is clear here, I hope. We can go to the another slide, and we can repeat again these stories. So in this case, we want to calculate 64 elements of result matrix C, which needs to be calculated, and 64 threads for that 64 elements, 64 threads need to be formed to calculate all elements of result matrix C. So what are we doing here? Of course, we have x-axis, and on this x-axis we are going on the x-axis and picking these columns or index of these columns, and when we're going through epsilon axis, we are picking up these row indexes for the row for the threads. So every thread here have its own index in y, threadIdx.y, and threadIdx.x for column in which its position. So when we create, of course, when we from the kernels we create threads, they are like now matrix of threads, let's say, and they have its own indexes. When we form these kernels, every one of these threads actually have assigned index on the epsilon axis and x-axis, which helps to identify that which thread inside this matrix of threads is, or 2D array of threads is assigned to them. So every of these threads have its own index, and how it's done in program. This is theory, and this is how we write it down. Of course, we define some, let's say we can put some variable or constant here, and then we created 2D struct with this dim3 threads per block. This threads per block is a struct variable with x and epsilon axis. So also don't forget that we are putting here x, what's need to be dimension for the x according to this rule, and also in epsilon, which x epsilon, and for epsilon we are going in this direction to, of course, avoid confusion, because in the program, when we writing program, this is x, this is epsilon, but in reality, epsilon is going through the epsilon axis, and we're picking up the threads, and max threads, thread number in this direction is given here. If these are, let's say, not the same values. Also, we calling the kernel function. And we say that threads which will be formed for that kernel function will be set in one block, and threads per block is actually n times n, or 8 times 8, so it's 64. We have 64 threads per that one block, which are put it in 8 in x direction, as it can be seen here, and 8 in epsilon direction, which can be here. Also, indexes are going from the 0 as usual is in this address arithmetic. So um, if we want to pick up, let's say, or assign for a specific thread, let's say we have these built-in variables and we want to use that variables in x and y. Yeah, this should be rows and this should be columns. One mistake again, but no problem. Let's say for specific for a specific thread, we have its own coordinates. So for that coordinate in threadIdx dot epsilon, we assign that column row which is in which that element is. Let's say this is the element. We assigned to this row variable, assign that value, and to the column we put threadIdx.x for picking up specific column. Let's say if this is the element, so this is the row we put here. This is the column we put here. These indexes, so we can use these values for the calculation of the respective element C of that result matrix C. Of course, everything is inside the rules of matrix multiplication. So for each thread created out of kernel function, we have fixed indexes, which we put in here in row. We pick up some, we have fixed index for the specific thread, and we pick up that index and put it as a row. For picking the specific row, as we said in starting or input matrices A, and of course index for threadIdx.x is put it in a column because we are picking up the column for the matrix B to do this multiplication and form the element C. But all these indexes are actually in some order related, as you can see. So what do I want to say with this is that we have same index for example, for the row is the same index for the thread, and the same index for the matrix row of matrix A, and similar to the matrix B. So we have column index for the element C, which is in result matrix, which is the same as the threadIdx.x for the index of thread, and also same index is inside the input matrix B for the column. So these in the way these three are, let's say, same indexes in let's say different imaginary objects. So also matrix multiplication rules, we picking up element from the row and from the column, we multiply it, we put it in a sum, we put it in a zero sum, and then use that sum and add it again with another multiplication, which is next, and then with another multiplication, always transferring the sum. So we need the program way to do it. Of course, we set the sum as a 0 at the beginning, And going through these all with the K, we are going through all these indexes of row and column. Row is from matrix A and column is from matrix B. Picking up specific elements and use address arithmetic here for the elements of the row and for the elements of the column in matrix B, and this is in matrix A. And also to use the device or GPU elements or components properly, and this is CUDA core. One of these operations is executed in one CUDA core and stored in sum, so variable sum. So every time we have after this, we store this in same direction where we start with, and that's variable sum. So this one operation is executed by the CUDA core. Then we pick up this sum and another. This is again in CUDA core, and this is, let's say, sequential business, because we need to pick up one by one by one by one by one. In this case, of course, because we are expecting this value to be transferred in another addition. And so on. So, but this is the way, and where we have for loop, we expecting something to be sequential business, but not parallel. But this one, yeah, this is executed on CUDA core. What is parallel? Parallel is for every specific elements we form the threads. So this ending element for every and each one of them, and there is 64 of them, we make threads. But this is execution inside CUDA, so so not to be mixed. And this is sequential job because we have for loop. What we can yeah, we can repeat these stories about addressing and how we pick up these. Indexes. So we came to place when where so the number of the row times number of the elements, it helps us to skip on the specific beginning of address, which is beginning of the row. And with the K, we are picking up all these elements which we used as elements of the matrix A, which is input matrix. And also we want to find a way where we're picking up specific column. So we gave a specific, let's say this is the beginning of the column. We have that address, and with this k times n, we're skipping up 8 addresses and go to next address in column to pick up another element. And you can see it's a little bit tricky to understand, but it just for wait for the picking these elements and make the multiplication in every of them, and then we when we multiply them, we add them to the sum in each loop. Yes, in general this is parallel, but this part of the elements multiplication and adding is a sequential job, so it's like a classical job, but done just in CUDA cores. But what is the parallel? Parallel part is for each of these elements of C, we forming these threads. And then when we finish this multiplication and adding of these elements, which is the way we doing matrix multiplication, pick up one row from one matrix, and from another matrix we pick up column, we multiply and add them. And when we finish that, we have that element. So sum is at the end of this process. In for loop, we have completed the sum, and we put it in a finalized element C, of course, with this let's say a row address arithmetic with which we picking up specific element. So we find the row, and then on the specific column we pick up where final position for that element. So I hope that we understand it well what is happening here, and maybe yeah. This is a little bit better picture of what we said previously. We have example of thread indexes which are representing coordinates of specific thread. So we said that this is, let's say, that specific thread, and we have specific coordinates. So this row, we have this thread index, which is 5. We said that here. We have that we are talking about this example specifically, and we have a column index which is 1, and these are thread index for on y axis of that thread, and on the x-axis for that specific thread. So we have these indexes which are corresponding to the indexes of the that element in result matrix C. And so how we calculate this? Of course, from the matrix A, which is represented here, we picking up these, as we said previously, we picking up same row, and of course for this column of matrix of thread index or result matrix C, we pick up the same column, and we multiply respective elements and forming the element of the matrix C, which is task of this specific thread. So one thread is forming one element of the matrix C. Anyway, first entry matrix, that's this one is first entry matrix. First or entry matrix from which we are picking up row. We need to pick up a complete row 5 with the help of indexes, and that we are doing with the k, which is going through the 0 to 7, and that was done by this for loop in previous slide. Where exactly? Let's check it out. Yes, with this for loop we are picking up from 0 to 7. So to pick up all these elements from the row, and index k is helping to pick up all these addresses, so addresses of all these elements, helping to pick up all addresses of elements in row 5. And it goes with the help of equation for addresses determination. So with this equation we determine the address of element. So, and it goes with the help of equation for address determination of elements in reference to starting position of address A. So this is here, let's say, first element is having this address E. And from that position, if we want to go, let's say, in row 5, we skipping up n row times n addresses to come here. And if we want to pick up all these elements, because row times n are positioning us here in sense of addresses, and if we want to pick up all this, we are going to the k is equal to 0, 1, 2, and 7. And similar to the second matrix from which we are picking up the columns, second entry of matrix B, we need to pick up complete column col 1 with the help of index. Again, we are because same elements must be here, same number of elements must be here in row and here in column, and we need to find a way to pick up addresses and elements on these and values on these addresses through some address arithmetic. So we need to pick up complete column call 1, so all these elements from this column. With the help of index k, k is helping us to jump on these elements. With the help of index k is helping to pick up all addresses of elements in column 1. So as we said, k is helping us to pick up all these elements in column 1, starting from this position, and we will see what is the equation for that. And it goes with the help of equation for address determination of elements in reference to starting position, starting address A. So this is starting position, or this should be B. Sorry. So this is starting position of addressing elements of the matrix B. So we're picking up this column. So when we say column, we jump here, and how we pick up all these other elements. So we pick up this one, and if we want to pick up others, in same column we're picking up for the n elements. So from here to here we pick here for k is equal to 1, for k is equal to 2, we skipping up 2 from this point, from these addresses, we are skipping and going to we're skipping addresses from to k times n in accordance to beginning position. So we jump here and so on. So every time we increase key is equal to 3, we are, let's say, from a starting position of B, address B, or address of matrix B, we are skipping skipping all these addresses, coming here, and with the column we picking up a specific address. So this is how we pick up all these elements in the column, and we explain how we pick up all these elements. And of course, according to this procedure, which is shown here, and this is more clear explained in next slide, but we picking up respective elements and multiply them. So this is more, let's say, more visual way to explain this matrix multiplication, which is basically pure algebra, but let's remind ourselves many times as we can, so we can comprehend this process very good. And at the in the end, we say, yeah, this is the main function. We have and how we call it in the main program. Of course, we are defining threads per block inside the main function, and we use it here. Of course, there is the one block which consists of 2D array of threads. Dimensionality of that, let's say, array of thread is given here. So 8 as it's shown here. We put memories or pointers to the memory locations in the device memory or GPU memory for entry matrices A and B, and we also, for the result matrix, we put the pointer so we can store these results. This is the calling in a main function, and this is how we in total define it. Of course, name of the kernel, entry matrices for multiplication, and the result matrix, which is output, and v for each element in matrix C. We you each thread will calculate specific element of the matrix C, and they have respective indexes for the rows and columns for that element, and for doing these operations, which are in correspondence with the thread indexes on y-axis and x-axis. So there's some, let's say, not equity, but there's some, what's the term? There's some equivalency between these thread indexes and indexes rows and columns inside the matrix C. And for specific row and column 4A, 4B, and 4C, we are picking up all these elements in rows and columns and store it in a sum, and we define here sum as a neutral element, so it doesn't affect us when we're forming the rows, when we're forming the elements of the result matrix C, and when we go through all rows and columns of A and B respective, we multiply them, add them, and on the end we picked up all the elements and sum them up, and we form, actually, according to the algebra rules, we form the element of the matrix C, and which is stored in sum, and at the end of the fourth cycle we put that sum into this specific element, which is of course using it's this is if pointer is pointing this address for specific row, we're picking up the row, we are skipping these addresses so many times. Let's say if row is 3 times n, so 3 times n is skipping, and then because this one is 0, we're starting from here, and for the column we find specific, let's say, column, and that's our index of thread, and that same index is for the element C, and we put this final sum in that element, because it's all done by the rules of row and column multiplication for the matrix multiplication business. So that's all for this. I hope this this helps you to better understand how to use the array of threads inside one block to faster do your job and go through it. And this is just entry point for the tensor core matrix multiplication, which will be similar in some way, but also different. But this is good entry point to the array of threads. So until next time, stay tuned.